concerned with the concept of shifts in data and the method of assessment, the resistance of models to shifts, which is called worst case risk. In this part, we will consider a method for creating multidimensional time series using deep generative models. We will call the created time series fake data. And we will show that using fake data, it's possible to supplement the original sample, original set, and improve the assessment of the stability of models to shifts. Okay, we will starting by looking at what generative modeling is. I start with all machine learning models are usually divided into discriminative and generative. In this picture, we see the general idea of the difference between these approaches. Let's look at a data set of, for example, photos of cats and dogs. Imagine that each photo has some kind of vector representation in a certain space. A discriminative model can solve, for example, the problem of determining who is a cat or a dog in a photo. Then such a model will construct some separating surface in this space, as we see in the figure. The generative model will construct a general vector space of cats and dogs, which can be described by a probability distribution. And using this distribution, we can sample observations and get new photos of cats and dogs. In this table, I listed the main difference. So, discriminative models predict the label based on the example. Generative model describes the complete distribution of data over a given subsample. The discriminative model learns the conditional distribution of labels according to the given example. The generative model learns the joint distribution of labels and examples, or only examples if the data is unlabeled. Examples of tasks that discriminative model can solve. Is the cat in the photo, or how old is the person in the photo, or what are the most likely number of tourists next month? In all these tasks, we predict a certain label. A cat, age, an age, or the number of tourists, according to the given example. A photo of a cat or a dog, or a photo of a person, or the history of the arrival of tourists in previous years. Example of task that generative models can solve: create a photo of a cat that looks like the average value between photos of two other cats, or create a photo of an avocado archer, or, for example, write an essay on global warming. At the same time, we do not have a photo of such a cat. We don't have a photo of armchair with avocado form, and we have no an essay in the original dataset, trained dataset. So our task to build a distribution from which we can sample new examples. Okay, deep generative models use neural networks. They are very different, but their work can be represented in such scheme. We define a certain latent space, denoted by the letter Z. This space has a simple low-dimensional distribution. It's a well-known distribution, for example, Gaussian, and we can easily sample from it. In the data space denoted by X, or X and Y if the data are labeled. On the contrary, it has a complex multidimensional distribution, and it's not clear how to sample from it. But in the middle, we see a neural network, which is essentially a function that takes a sample from the latent space as input and translates it into a sample from the data space. Okay, now let's move on to creating time series. Let's consider the process of generating time series using example of the generative model is a generative adversarial network. The general idea is shown in the picture. We have two neural networks, a generator and a discriminator. The generator takes a vector from the latent space as input and returns time series. The discriminator takes a time series as input and returns the probability that the series is fake. Let's denote the time series by the letter X. During the training, we optimize this function. That is here, this function. That is according to the discriminator, we maximize the log likelihood from real data. And according to the generator, we minimize the logarithm from 1 minus the likelihood from fake data. This is fake data. GAN can be created on the basis of different neural networks, but in this tutorial, we will analyze the work of GAN where the discriminator and generator are temporal convolutional network, TCN. The principle of operation of TCN is shown in the picture. We see that the sum sequence is blue circles. Another sequence is input, some sequence is input, and another sequence is output, is orange circles. That is, it's a sequence-to-sequence modeling. For the generator, we input a sequence of vectors from the latent space, and we get a time series. For the discriminator, we fed time series to the input, and we get a sequence of probabilities, likelihood, whether this series is fake. Advantages of TCN are, we see that the information from the previous layer is transmitted over the entire larger set. The size of the receptor field grows exponentially. That is, in the first layer, we see the size is 2. In the next layer, we see the size is 4. And the next layer, we see that size is 8, and so on. This allows us to take into account both short time dependencies and long time dependencies. Such a neural network can process time series of any length. For example, once trained on short time series, this neural network can be applied to long time series. And third, we see that the information on the next layer comes only from the past. That is, it doesn't allow us to look into the future, and then model learns cause and effect relationships in the data. The main parameters of TCN are for the generator. This is the number of input channels, that is the dimension of the latent space, the number of hidden channels, which should be sufficient to describe the complexity of the data, and the number of output channels is equal to the dimension of time series. For the discriminator is opposite. The number of input parameters is the dimension of time series. The number of hidden channels is also selected with respect to complexity of the data, and the number of output channels is 1. That is, we need to get one number, the probability. Let's move on to creating time series. Now install the dependencies. Hello, are you hear me? My connection is unstable. Do you hear me, someone?
Hi, Vitaliy. Yes, I've been able to hear you.
Okay, thank you.
Yes.
Yeah. So we install import libraries and download the dataset from the previous part of our tutorial. This is the energy consumption dataset, and let us look at the time series trajectories by components. As we see, we have some time dependencies. For example, here we see some short dependencies and long dependencies, like seasonality of our time series. And different components have different dependencies. And we split the dataset into train, validation, and test periods in such way. The first 70% of data is train set, next 15% is validation data, and we have another 15% of data is test set. And we are looking for the shifts that can be near the validation period. Here we apply a standard scaler for training stability, and we download we split the dataset into batches, where each batch consists of few time series samples. And here we define sliding window dataset. Sliding window means that we have, for example, we can imagine some window with fixed size, and we slide this window from left to right, and we see what we see time series which includes in this window, and we save this time series into dataset. We select the window size is 200. Let us define the sliding window dataset and the data loader to train our network. The shape of one batch is 64 is the number of samples in one batch. 200 is the length of time series, means each sample has the length of 200. And the dimensionality of time series is 7, that is 7 components of our time series. Next, let us define our TCN GAN model. We have latent dimension is the latent dim, the dimensionality of latent space, which is multivariate normal distribution. Hidden dim is number of channels in the hidden layers, and target dim, the dimensionality of time series. And the number of layers is selected by num layers parameter. And finally, LR is the learning rate for the optimization step. The values of parameter can be tuned using some methods like grid search or random search. Here we just apply the predefined parameters. And GAN is known as unstable for training, so it's very important to monitor some auxiliary metrics. For example, the discrepancy between minimum of real and fake time series, between maximum of real and fake time series, and between mean of real and fake time series. Here we see how this monitoring can look, and we see that the more steps we done, the best metrics we obtained. And in our tutorial, we skip the training part to save time. In just a case, I say it takes about 10 minutes on training on NVIDIA V100 GPU. Yeah, here we just load pre-training model from a checkpoint file. Yeah. Let us define the model and let us sample the time series of the size 1000 and look at the pair plot of fake and validation data. Yeah. As we see in the pair plot, the blue circles are fake and orange circles are validation data. We see that fakes looks pretty similar. Many of relationships are kept in our data set. By the way, we can change this parameter, temp. It's actually the variance of multivariate normal distribution. For example, we can set 2 and create new fake data set. As we can see, we obtain more risky data, which includes much more outliers. And we can change this parameter according to our decision how risky model we can generate. In our tutorial, we will use the temperature is 1, which is the normal distribution, but it can be changed. So let us also plot the trajectories of fake time series. Yeah, the black lines are validation data and the colored are fake data. As we see, it looks pretty similar in each component. And yeah, we can see that fake time series are similar to real ones. But if we want, we can evaluate some metrics, such as autocorrelation function error, that can give us numerical estimation of closeness to real-time series. For example, we can see the paper, which is one GANs, to more information, to give more information. Conclusion so far, we split the data set into train, validation, test sets. Next, we trained a GAN model on the validation set because we are looking for shifts in periods which close to the validation period. And then we create fake time series and visually check that are similar to real ones. Okay, now we go to worst case risk on fake data. Let us again download the data set and prepare it for regression task. We want to predict the OT feature. Let us look in the data. Yeah, so we have original columns in our data sets, and we also add day of month, day of week, hour, month, and OT-1, which is the value of OT is oil temperature in one step ago. And our task is to predict OT using all of these features. So let us create the fake time series using our generative model, and then prepare this fake data to regression task. Here we see we choose the sequence length as length validation data multiplied by 10. So 10 times more data than in validation set. We select the temperature as 1. Then we make inverse transformation from normalized fake data to the original scale. And then prepare data set, which is pandas data frame, and create new features in similar way for the real data. Okay, we can see that the data set looks similar, and we go to the creating train validation test and fake sets. We select target column, which is OT, and feature columns, which are all columns with difference of target column. Then we create X and Y data sets, and create X train, Y train with respect to our validation threshold, X validation and Y validation with respect to validation threshold and test threshold, and then create X test and Y test using our test threshold, and finally we create X fake and Y fake using our fake data set. Okay, run the cell. Next, we train a linear regression model and calculate the error. As we can see, the error on validation set is close to error on fake set, which means that the model cannot detect much discrepancy between them and produce the similar error. Okay, next we define immutable and immutable variables as in previous part of our tutorial. And we calculate worst case risk on validation data. As we can see, the the value of the error is decreasing with decreasing the population subpopulation size, and we see that the actual error on test is here around 0.65. But if we use the same thing on fake data, we obtain another result. Yes, I remember this is the last one, progress bar. Oh no. This one is last, I believe. No. 1, 2, 3, 4, 5, 6, 7, 8, 10. 10. 1, 2. Okay, yeah, we got it. We got the result. Worst case risk on fake data set. We see we can obtain the narrowed uncertainty interval for fake data, and that means that we can more precisely assess the robustness of the model using such fake data. Okay, it's the final part of our tutorial. What can we see? Generative models produce realistic data that can help to estimate model robustness to dataset shift. However, it brings some disadvantages. The first is the fact that it's hard to find the best hyperparameters of our neural network, and it's hard to train such a deep neural network as GAN and other generative models also hard to train. The second disadvantage is it's hard to estimate how close the fake time series to real ones. There are many metrics, some of them more popular, but in image domain or video domain, but no scientific standard so far for time series domain. The third is we assume that generative model can produce original data distribution. So if it cannot produce the original data distribution, our evaluation will be unrealistic also. And conclusion, so in our 2 parts of tutorial on model validation by worst case risk method using deep generation models, we consider in the first part the concept of supervised learning and the overfitting problem. Then we considered the dataset shift problem, the definition of the dataset shift, and the examples in real life. Then we downloaded the data that contains the time series with energy consumption. We split the data into train, validation, and test periods and observed shifts. Then we trained the regression model to forecast the oil temperature. We investigated that quality is reduced in the test set. And then we evaluate the model robustness to dataset shift using worst case risk. In the part 2, we consider the concept of generative learning or generative modeling. Then we created the GAN model based on temporal convolutional network to generate time series. Then we trained the GAN using validation data and generated fake time series. Then we visually evaluated the quality of fake time series, and we evaluated the model robustness using fake data and got a more accurate estimation. That's it. Thank you for your attention, and I will happy to answer your questions.